Hello, my name is Zane, and in this video I'll give a high-level overview of how I use an STM32 microcontroller to generate a PWM signal with dead time to drive a half-bridge circuit. So this is the STM microcontroller here. If I can get it to focus. This is the STM microcontroller here that was used to generate the dead time. And in this video, I'll show how I use the STM32 microcontroller to generate PWM signal, complementary PWM signals with dead time to drive a half-bridge circuit. So for this project, I've got the STM32 board set up here, and I've got an Arduino shield on top of it. The Arduino shield allows me to connect my UART adapter here for serial communication to command the PWM on and off, and then I've got a logic level translator here to shift up from the 3.3 volt of the STM32 up to the 5 volt output that I need for my my circuit that I'm driving. Okay, so the first thing I want to go over is the high-level overview of how this all works. So I'm going to look up the reference manual for this microcontroller. So it's the STM32 F446RE reference manual. I'm going to open it up. And so this is the reference manual for the STM32 F446 family of microcontrollers. We are looking for the section on PWM. So I'm going to Control F, PWM, and it pulls up quite a few different pages here. I want to see if I can find a high-level overview of the PWM peripherals on this microcontroller. I'm not seeing it here. Let's just scroll down. Okay, so here is an introduction to PWM on TIM1 and TIM8, which are the advanced timers on this microcontroller. So here's TIM1 and TIM8 functional description section. The reason that we want to use TIM1 and either TIM1 or TIM8 for this project is because these are advanced timers, and they have the ability to generate complementary outputs. So if we look here at some of the features of this microcontroller, we can see that it has the ability to generate complementary outputs. Okay, here we go. Complementary outputs and dead time insertion. So we can see that the advanced control timers TIM1 and TIM8 can output two complementary signals, and why this is important is because it will allow us to insert this delay, and this delay is will be applied to OCX and OCXN. OCX reference is the reference PWM signal. OCX will the rising edge will be offset by the rising edge of the reference signal by the amount of the delay, the time amount of the delay that we set. And the rising edge of the OCXN will be offset by the falling edge of the reference signal. So using timer 1 or timer 8 for complementary output generation, we will be able to generate this dead time signal pair here. Okay, so here is the STM32 Cube IDE. This window that we have pulled up over here is the IOC. This is where peripherals can be configured. So let's take a look at the clock first. We can see that it's either the APB1 or the APB2 that's going to control the timer TIM1 peripheral, and so we've got that set to 84 megahertz. Then here in the configuration tab, you can see that I've selected TIM1, and the clock source is the internal clock. And for channel 1, I've selected PWM generation channel 1, channel 1N. Out of all the options, I've selected this one. And this will load the settings for generating complementary outputs, the OCX and the OCXN that we looked at earlier. I've configured these settings for a 10 kilohertz signal, and so my counter period, my prescaler are set accordingly. I've got a dead time of 80, and this is a calculated value. My duty cycle is 50%, so that is the 8400 divided by 2. And the rest of the settings are configured for my application. Then if we go into the main.c, so we can take a look at our code, the configuration tool has put most of the code here for us. So it's configured the clock configuration settings. It's got this tim1 init function here set up with all of the code needed to initialize our timer. And then here I've got some code that will execute when a certain string is received on the UART bus. That's not necessary for your application. All that's really necessary to get the PWM signals going is this line here to start it. This will start the output compare on channel 1 and channel 2. And to stop it, you've got these two functions here. And so that's all you need to generate the PWM output. And then for my application, I've got a little terminal window here that you can send UART commands to. I've got a UART adapter hooked up to my computer and connected to my microcontroller, and when I send this command, and this is an echo, this is not an echo, this is a return received command from the microcontroller. It's letting me know that, hey, I've got the command and I am starting the PWM. And we can take a look at the oscilloscope and take a look at that, what those signals look like. Alright, so here at the oscilloscope you can see that the signals are there, channel 1 and channel 2 on the microcontroller. And you can see the dead time here where both channels are low for a certain amount of time. So that's it for this video of generating PWM signals with dead time on the STM32 microcontroller.